All right, guys, can you hear me? So we are at the, just put up what we are at. We have been doing the Millstone scheme. We did the Brownian bridge. The last thing I want to do today, yeah, it's probably going to be the last thing we'll do today, is going to be risk measures. So an application to risk measures. Not that this class here is about, it's not about risk measures, but there's a nice application of simulation to risk measures. So risk measures, this has been a huge topic up to the crisis in 2007, 2008 to the crisis in 2007. Interestingly enough, after the crisis, it kind of died down. There was a huge topic up to this crisis, together with credit derivatives. By far the biggest result in this you can find in a paper about coherent risk measures. So let me just show you the paper. Show you the paper. Look up coherent risk measures. So you go to Wikipedia here, and you go down to the by far the most influential paper. Is this one here by Arsene Delvan, Eva and Heath in '99. So this is written some 20 years ago. And as you can see, just by scrolling down the list of coherent risk measures, so there are examples: value at risk, average value at risk, intraparty, blah 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 blah. There's no end to it, and there are many more than the ones you see here. So coherent risk measures, this is a class of risk measures, and a very popular risk measure is this value at risk. And unfortunately, this value at risk measure is not coherent. So what I'm going to be talking about today, I'll talk about a few of them. I'll talk about this value at risk, and I'll talk about the tail value at risk. Those are the ones that are very easy to calculate using simulation. There's another one that I'm going to mention in the end. This is called expected shortfall, and it's not on the list here. I don't know why it's not on the list here. It should be on the list. So I'm going to talk about a few of them, but as you can see, there are many more. They all have like different properties. I'm going to focus on the ones that make it easy to calculate using simulation. Okay, so coherent risk measures. This was a class of risk measures that got developed in the late 90s, and so the most popular. So the most popular measure is called VAR. So it's written like this: V little a capital R. This stands for value at risk. And it's not, I'm not going to talk about what coherent means, but the thing that you need to know is that this is not coherent. it fails, and we're going to see that it fails the sub additivity. We'll see this in a minute. Right, so sub-additivity is about diversification. Value at risk does the opposite of diversification. It incentivizes people not to diversify, and this is a problem, and that's why it's not coherent. But let's talk about value at risk, because it is really a measure that is being used to this day all the time. Okay, so you're gonna say your profits and losses. Let's say your profit and loss. This is called P&L as a density. So you're looking at profit and losses, and you look at the density. Right. So out here is where we have profit and loss. So profits are on the right, losses are on the left, and you look at the density. Who knows how it looks like? Maybe it looks like this. Right. So the mass underneath the graph is 1, and so what you do is, if you're looking at a 95% VAR, value at risk, then you go out here somewhere here, and this will be your value at risk here, and then this area here, there will be 95% in it. And to be accurate, this here is a minus. So value at risk is a positive number. So there are endless problems with this measure, but still, you can get a 95%. That number here can look like this. It could also be much more messy, right? You could have that your density function would look like, and it could be the same value at risk, but maybe this thing would go down like this, and then it would go up like that, and then this would also have 95%. So you're only reporting that one number, and you don't really know how the losses look like. So value at risk. You're only reporting one number, namely this intersection here, and then if you take the sign away, you swap it. So this will be a negative number, right? So this will be minus R would be a positive number. So using Monte Carlo, this is easy to calculate. This is easy to calculate. And let's just show you what I mean when I say it's easy. It is really very easy to calculate. Let me switch over to MATLAB again. Okay. So here's my little script. Here's my little script for calculating, just giving an example of value at risk. So what am I doing is I have this is my profit and loss. It's just a very simple model for profit and loss. Say that profit and loss follows this SDE here. It's just BT to BT. That was exactly what we saw. Right, this here is equal to, what was it? BT squared divided by 2, BT squared minus T divided by 2. Right, that was the formula we had for that Brownian integral. So that's just my my simple model for a profit and loss. So what I do is I have I'm looking at a period. The length of the period is 1 year. I'm looking at 100 time steps. And then I'm just growing paths. I'm growing 1,000 paths here, so maybe I can just grow a 10 paths, and we can look at a picture of them. So I'm plotting these profit and loss realizations depending on the path that I'm looking at. So let me get that going. My name. There we go. There are my 10 paths of the profit and loss function I'm looking at. So this is BT squared minus T, and you can see some of them are positive, some of them are negative. There can be losses, there can be huge gains. And now there's something else it doesn't like. Why does it not like this? I think I had 1,000 of this in the chart. 1,000. There we go. So if I do 1,000 paths, I'm going to get a picture that is much wilder. Okay, so to calculate the value at risk, what I'm doing is I'm looking at all the values that I get out here at the end. Right, so I have 1,000 paths, so I'm going to get 1,000 values out here at the end. I'm getting 1,000 values out here at the end, and I want to create that density structure that we had on the document canvas. So what I'm doing is I'm looking at these. Maybe I should not do 1,000. Let's do 100, and then let me look at the values sorted that I get out here at the end. Right, so here I'm looking at all the values right here at the very end. So I have 100 of them, and I sort them. So here are my 100 values. These sorted from smallest to biggest. Right, so it goes down to minus a little bit more than a negative a half. Right, so the lowest value is down here, a little bit more than minus a half, and then up to the top one. The top one is a little bit bigger than 4. You go down and check, it's a little bit bigger than 4. So I sort them. So I have 100 values here. If I'm interested in the value at risk, then what do? I decide on how much percentage I want. If I'm looking at 90, then I'm going into my list. I go 10 steps back. So this is, I mean, there's 7 in each, right? So this is 7, 8, 9, 10. This here is my value at risk after I swip the sign if I'm looking at a 90% value at risk. Right, so the value at risk at 90% level will be 4,759. If I'm interested in it at 95%, then I'll go back to this number here. That would be my value at risk at the 95th percent level, and 99 would be this one here. And so this is what I'm reporting, just these numbers down here after I switch the signs. So it's quite straightforward to do this at using simulation. Just sort them, and then you just go however far to the left that you want, depending upon what confidence level you want to be at, 90, 95, 99. And of course, there's no, I mean, I can do 1,000. This is what I had when we started out. I don't want to plot 1,000 because it's going to take up, I want to print 1,000, but now the picture gets a lot messier, and the principle is now this, I mean, it's the same. I would have 1,000 values up in the matrix, and depending on how far to the left I want to go, I'm going to get different values of this. So it's quite straightforward to calculate. Okay, so that's good. It's easy to calculate. So what's the problem with value of this? So it is really easy to calculate. I just showed you it's not a problem to calculate, but the main problem, so the main problem is that var can discourage diversification. So in math, it fails to be sub-additive. Okay, so let me give you an example of this. Why does it fail to be sub-additive? So say that I have two securities. Two securities, yeah, independent. Probability of default. Each has say 4% probability of defaulting. If it defaults, there's a recovery. Maybe we should just plot the P&Ls. This here is number 1. This one here is number 2. I'll plot if it defaults, it'll go down to minus 0.7, so that will be the loss. And then otherwise, it'll just be 0. So a lot of upside, but here we'll have 4%. And this one here would be, well, it'll be the remaining 96%. It might be a bit, there's not a lot of upside here, but we could split this 96 into 2 bars, and I could have half of that. That would be like 48. I could have it 0 and then 48 at say 1. This is not really so important because we only care about the left here. So I just put everything at 0. And then the same thing is over here for the second security. So it can go down to minus 0.7 and then 0. That would be 4% here. And then there would be 96% here. If I look at the value at risk for each, that'll be 0, because I need to find a point such that I have 5% at and to the left. So value at risk for each is 0. And that's why the 4% is important. Had the 4% been like 6%, then the value at risk would be minus 0.7. So the value at risk for each is 0. So now we look at a portfolio. So now we're looking at a portfolio of half of each security. Okay, so now, what can happen is that we'll have a different P&L for the portfolio. So you have a 0, and then half of 0.7 is 0.35. And then over here we'll have, if both of them default, it will be 0.7. And this is my 0. So now for the portfolio, there'll be 3 possibilities. Right, so what is the probability that they both survive? Probability of both and not defaulting. This is where we're going to use that they are independent. Right, so that will be the probability of both not defaulting. That would be 0.96 squared. And so probability of at least one default well, that would be 1 minus 0.96 squared. And if I manage to do this correctly, this number here is 92.16%. And this thing here is going to be like 7.84%. Right, so now it pops over 5, which is the key thing. Right, so here we will have 92.16. And then these two here will have to split the 7.85. And so if you look at the probability of both defaulting, and that would be a 0.04, but each have 4%, so we need to square this thing. This will be 0.0016. So this is tiny. This is 0.16%. And of course, given that this one and that one has to add up to 7.84, we can figure out what this one here is. This one here is 7.68. So if I look at the value at risk for each, I get 0. If I look at the value at risk for the portfolio, then it's going to be minus, so that minus has to get changed. You always have to flip the sign. So it's a 0.35. So what's up with this sub-additivity? Like sub-additivity means that the sum dominates, and here it does not. Right, so what we're going to have is that the value at risk. So the value at risk of 1/2 number 1 plus 1/2 number 2. Right, these are my two securities. I took a half of this one and a half of this one. The value at risk for this one was 0.35. But if I do a half of the value at risk of number 1 plus a half of the value at risk for number 2, they were each 0. So this here is equal to 0. Right? So the sum does not dominate. So VAR is not sub-additive. There's somehow more risk involved, according to the VAR measure. There's more risk involved in the portfolio than there is in the individual components, right? So it discourages diversification. So that's the main problem with value at risk. Probably some of you have seen this before. The next thing that one could then do is move over into these, look at other risk measures. And there's one called CBAR. Or you'll see words like expected shortfall, and expected shortfall, and CVAR. Some people also call it AVAR. So let me talk about this one here. This is just the average. So you have your tail. So you have your tail. Here you have your minus your value at risk. And so what you do out here, this is where you have your 95%. So here you take an average. So take an average. Take an average over here to get this C bar, also called A bar. So you take an average out of the tail. And so let me show you how to do that. This is also quite easy to do using simulation. So we have our what, 1,000 paths. And so what do you do in C bar? If I just look at, say, 100. So C bar, what you do is you take the mean out in the tail. You take the mean out in the tail. So we can run it. So if I'm looking at the C bar, if I'm looking at C bar at 90, and we print them out, we can look at them. If I'm looking at it at 90, I'll go up in the table. I'll go out to position number 10. So 7, 8, 9, 10. So I'll go out here. If I remove the sign, I'm gonna get value at risk. If I want to go get C bar, what I do is I take these 10. I take these 10 and take the average. So that is, and then you remove the sign again. So you always remove the sign so you get a positive number. So by taking the average of these 10 here, then I'm computing that number here. So that's also not difficult to do. I can also do it in the example. And of course, if you're looking at it at the 95%, then you're going further out in the tail. You're taking the average not over 10, but only over 5, and so on. Of course, if you're all the way out here in the end, then you're only taking the average of one number, so it's just a number. Let me show how to do it in this example here. So in our example, so back to the example, if I'm looking at the portfolio C bar, then I have my three values. I remove the sign, so it's 0.7 and 0.35. Okay, so I will take 0.7 times the probability of 0.7, so that's 1 point. That is 0.16%. So this is 0.0016 plus, and then the other one minus 3.5. Remove the sign. 3.5 take times 0.0768 divided by these two numbers added up. That was that one we had over here. 0.784. And you calculate this, and you get 0.3571. And of course, if I look at the two securities, their C bar, the tail is everything, so it's just the expectation. It would be 0.04 times 0.7, in order to make it consistent. 0.7 times there were 4 probability, and then it was 0 times 0.96, 0.028, and the same thing for the other one. So again, you see when you add them up, if I'm looking at 1/2 C bar of number 1 plus C bar of number 2, I'm going to get these two numbers added up, divided by 2. You're again seeing that it has the wrong effect. So this is not subadditive. The thing to save today is that this is this lemma that says that for continuous, so write it out carefully, for continuous distributions, here these distributions we're looking at are not continuous. For continuous distribution, C bar equals this expected shortfall and is always subadditive. Indeed, this expected shortfall, which I haven't talked about. Indeed, this expected shortfall is always coherent, whether or not the distribution is continuous. Right. So the lemma says, even though I have talked about expected shortfall, I haven't talked about coherent. For continuous distributions, C bar is subadditive. And so when we're looking at these plots, it's very easy to compute C bar, and it's good enough because for those paths that we're looking at, we will have a continuous distribution because of Brownian motion. We got a little bit rushed here in the end because we ran out of time, but risk measures, in particular, value at risk. I mean, this is something that a lot of people use. So here's a little quick overview of what it was. We looked at some examples, and I wanted to look at this application because simulation makes it very easy to compute. And you can see there's not really a big difference in terms of calculating value at risk versus calculating the average over in the tail. Like whether you compute this number here or you compute the average over the remaining numbers, it's, in terms of computations, it is tomato, tomato. And by computing this value, this average over in the tail, at least when the distribution is continuous, you have a much better measure because you don't discourage diversification, right? You want a measure that should encourage diversification, right? It should be, you want risk to be spread, and then so the measure you're using should encourage you to spread out your eggs instead of putting them all in one basket. Okay, we ran a little bit over time. Are there any questions here at the very end, or are we all exhausted? Are there any questions or comments before we call it quits? If not, we will have office hours tomorrow morning at 9 o'clock, and the TA, I saw the TA has graded the first homework at least, and he also has office hours today and tomorrow. And any questions or comments? Otherwise, I hope to see some of you tomorrow morning, and if not, I'll see you next week. Okay, I'll see you next week.